And welcome to the MCA Services YouTube channel. In this presentation, we're going to be looking into sample degassing and demonstrating why it's such a critical part of gas adsorption analysis. But I'd like to start off by just saying thanks to our Year 13 work placement students, Ethan and Philip, who undertook all of the analytical work you're going to see here today. We have other presentations on gas adsorption analysis, and they cover the analytical theory, the technique itself, and the interpretation of results, and do go and have a look at them if they're likely to be of interest. But in this presentation, we just briefly consider the gas adsorption isotherm, and that's shown here with the adsorption branch in red and the desorption in blue. We use the technique to characterize a sample porosity, or the porous nature of a material, and from the various parts of the isotherm, we can obtain varying information. At the low end, low relative pressure end, we can look at micropore volume, area and size. A little higher up on the adsorption isotherm, we can look into specific surface area, most commonly BET surface area. From the very highest point, highest relative pressure of the adsorption isotherm, we can assess total pore volume. And from both adsorption and desorption, we can look into the pore size distribution of mesopores and small macropores. And the relative shapes of the two parts of the isotherm can tell us an awful lot of information on the pore geometry that's present. But why do we need to degas a sample before analysis? Well, let's consider a single solid piece of material with just one pore within it, as shown here. If we want to measure the specific surface area, we're aiming to cover the surface of the material and the internal walls of the pore with a single layer of adsorbed atoms or molecules, called the monolayer. But now let's consider the same sample material, the same pore, but this time in the presence of a volatile material, such as moisture or a solvent. Now, gas adsorption analysis is typically conducted at cryogenic temperatures, 77 Kelvin being the most common as liquid nitrogen. At this temperature, any extraneous volatile substances will freeze, and they will at least partially block, or if not completely block, that pore within the material. Here we show it as being completely blocked, the worst case scenario. And when we proceed with the gas adsorption analysis, we can see that the adsorbed atoms can only now cover the external surface. They can't interact, can't access the interior walls of the pore. So with the sample free of extraneous volatile materials, we can use gas adsorption to accurately measure surface area and also pore volume and pore size distribution. Whereas when that pore is already filled with an extraneous volatile substance, then we're going to have errors, and we're going to have artificially low surface area, pore volume, and inaccurate pore size data. So degassing is the process of removing any extraneous volatile substances from a sample. It's usually undertaken immediately before analysis, and volatiles may be solvents remaining from sample preparation or moisture taken up during storage, and of these, moisture is often the hardest to remove. We investigated the effects of incomplete degassing and also the various options that we have here for degassing using a standard material, and that's shown here. This is a silica alumina, and the great benefit of using a standard is that it comes with instructions as to how exactly to analyse it, and also tells us how to select relevant data, and it gives us the answers we should be getting. For this material, the standard values are for specific surface area, total pore volume, and average pore diameter. And we started by analysing this material exactly following instructions. We obtained a specific surface area of 198 square metres per gram, a pore volume of 0.61 cc's per gram, and an average pore diameter of 11.4 nanometres. So we're comfortably within the specifications, and we can say with great confidence that our instrument is working properly and the methods are all good. The aim of this study was to investigate the effects of extraneous volatiles on analytical results and how successful removal of these volatiles was via various degassing options. We exposed the silica alumina to water vapour, and we did that by putting it into a sealed chamber at 100% relative humidity, so the chamber contained an excess of water next to the sample, and we left it there for 2 weeks. After that, we were able to determine that the silica alumina then contained very nearly 39% moisture by weight. For degassing, we should start by considering the methods that we could use. Somehow we need to remove the volatiles from the sample, and the easiest way to do this is by applying heat, so essentially boiling them off. However, we must be careful to ensure that the porous structure of the sample is not altered in any way, and for heat-sensitive samples this becomes of great concern. Essentially, there are 2 methods available to us, and that's flow degassing and vacuum degassing. These can be applied to a sample before loading into an analysis tube. For example, vacuum degassing can be undertaken in a vacuum oven, or after the sample has been loaded to the analysis tube using a special degassing unit. Consider both methods, and although we have an extensive range of degassing options here at MCA, we chose to degas using 2 special degassing units, a Microporous flow prep and a Microporous vat prep unit. We describe both here. We start with the flow degassing option on the left and the vacuum degassing option on the right. And in both cases, we can see the analysis tube with a sample loaded into the bottom of it, and the sample is the purple material. With flow degassing, we introduce a thin tube from the degassing unit, that's shown in red, and through that we pass an inert gas, such as nitrogen, helium or argon. We used argon during this study. With the flowing gas method, heat is almost always applied, so any volatiles become vaporized and they're removed from the sample, and then by the flowing gas stream they're removed from the entire tube. On the other hand, with the vacuum degassing unit, the analysis tube is connected to a vacuum port, and this time the volatiles are removed from the sample tube by the vacuum system. So we have our 2 methods. It should be realised, though, that the flowing gas method relies entirely on applying heat to remove the volatiles. They need to be vaporised from the sample, whereas the vacuum method is helped by the application of vacuum. And this is really, really useful when we start to consider heat-sensitive materials. The potential benefit of vacuum degassing is evident here. If we look at this graph of the boiling point of water against pressure under vacuum, we can see that as pressure decreases, so too does the boiling point of water. We know that at atmospheric pressure, water boils at 100 degrees. Now, a good vacuum pump and vacuum degassing system should certainly generate a pressure of around about 50 microns mercury, or 0.05 millimeters mercury on the x-axis scale here. At such a pressure, water boils at around about -50 degrees, and we can then remove moisture from a sample without applying any heat at all. And of course this becomes particularly suitable when we're analysing temperature sensitive materials. So on with the actual analyses. Ethan and Philip used both methods and applied a range of degassing temperatures and degassing times. Samples were then analysed and the results were compared to both the specification and also that original analysis we got by following the specification instructions. The table here shows a total of 29 analyses for both vacuum and flow. And the flow degas samples are shown in red and the vacuum in blue, with the exception of the very first vacuum degas sample shown in green on the top left. This sample was degassed to a minimal extent so that we could investigate the effects of analysing the material whilst as much of the pore volume as possible was occupied by moisture. Now it's really important to note that the easiest moisture to degas had to be removed before analysis. Our TriStar instrument that we used automatically evacuates the sample before analysis, and without any degassing beforehand, this moisture would be removed into the instrument and cause contamination. It's really useful that the vat prep degassing unit has a vacuum gauge, and this enabled us to stop the degassing of this sample just below the vacuum level that's applied by the TriStar instrument. This is typically a pressure of 1 millimeter mercury, and using the vat prep unit we found that this took about 15 minutes to achieve. This sample with minimal degassing is really useful for demonstrating the effects of volatiles remaining in the sample. This figure shows the adsorption-desorption isotherms of 2 samples. The red one shows the dry sample. So that's the sample that wasn't exposed to humidity and was degassed and analysed according to instructions. Whereas the green isotherm is the minimally degassed samples are still containing a degree of moisture. The isotherms are clearly very different. The green isotherm for the minimally degassed sample is much lower in terms of adsorption volume throughout, so relative to the y-axis. At lower relative pressures, this results in a much lower specific surface area. For the fully degassed sample, we obtained 198 square meters per gram, whereas we obtained just 46 square meters per gram for the moisture-laden sample. We can also see that the pore volumes are totally different as well. 0.61 cubic centimeters per gram for the fully degassed sample, and just 0.16 for the minimally degassed sample. The third specification for this material is that of average pore size. That's calculated via the BJH method using the adsorption isotherm. It's worth having a look at this. The fully degassed sample has an average pore size of 11.4 nanometers, whereas the minimally degassed is 12.9. In fact, we found that across the range of degassing conditions, average pore size was relatively insensitive to the success of degassing. It's not actually that surprising. When we look at this, the pore size distribution for the fully degassed sample may have an average of 11.4 nanometers, but the distribution itself ranges from approximately 2 to 100 nanometers. So the average value is unlikely to be particularly sensitive to slight changes. That said, the higher average pore size for the minimally degassed sample is being caused by an absence of volume in the very small pores, those below 5 nanometers, and this demonstrates that the smallest pores are often the hardest to remove volatile contaminants from. The other important thing is to look at the area under the curves. Now that directly measures total pore volume, and we can see how the red curve is laying so much higher than the green. So how much pore volume is actually being obscured by the presence of moisture in that green curve. So we can clearly see the effects of incomplete degassing on analytical results. The question then is how successful are the various degassing options at removing moisture from the sample and providing analytical results that match the fully dried sample. Given the insensitivity of average pore size, we'll concentrate on specific surface area and pore volume. It's worth noting that although the pore size distribution shows pores of approximately the correct size are present, it's their volume and also therefore their surface area that remain low for this particular material when contaminated with moisture. The degassing temperatures we have investigated are chosen so that they can be applied when considering a really wide range of sample types. Room temperature and 50 degrees degassing are investigated as they're applied to temperature sensitive materials. Given the relationship between pressure and the boiling point of water that we saw earlier, these can only really be applied to the vacuum degassing method. Higher temperatures, 100, 150 and 200 degrees, can be applied to both vacuum and flow methods, and they can be used to represent more thermally stable sample material types. We can start to have a look at the results. We're going to present a series of graphs like this one for BET surface area at various degassing times and temperatures. This is for room temperature degassing. Each graph has got a green bar on the left-hand side which shows the result for the standard material degassed according to instructions and not exposed to high humidity, and we'll call this the baseline result. This really gives us a target that we should be achieving for this particular batch using our specific instrument. The red line shows the minimum BET surface area of the specification. So that's 194 square meters per gram. We can see that the surface area does increase with the degassing time as more moisture is removed from the sample. But even after 18 hours, we still have not matched either the baseline and we remain under the minimum specification value. Moving on to degassing under vacuum at 50 degrees, we can see that we do exceed the minimum specification and we match the baseline sample after 12 hours of degassing. Complete degassing is probably going to be achieved somewhere between 6 and 12 hours degassing, although at 6 hours the BET surface area is significantly low. Given the necessity of complete degassing, it's best to degas for a long enough period to ensure that all contaminants are removed. And it's actually quite common to see instructions and specifications with 16 or 18-hour degassing, which equates to an overnight period. Moving on to consider vacuum degassing at higher temperatures, we can see that complete degassing requires 6 hours at 100 degrees and 3 hours at 200 degrees. The 150 degrees results are quite interesting since the 3-hour period appears to be just within the specification. But again, the longer period will be much preferred to 6 hours, as clearly more moisture is still being removed as the time is extended. And that exposes the remaining surface area of the material. Now looking at the flowing gas method, we can see that longer degassing times are generally required than for the vacuum method. 100, 150 and 200 degrees all require 6 hours degassing to exceed the minimum specification and approach the baseline result. This is perhaps unsurprising, as we're relying on the flow rate of the inert gas to drive the vaporized volatiles not just away from the sample, but also out of the analysis tube. This is quite an important point, as usually it's only the lower part of the tube that's heated, so the vapors will then have a tendency to condense on the cooler upper section of the tube rather than being driven completely out. For heavily contaminated samples such as these, it's then up to the operator to monitor this and remove any condensed material manually. So we now move on to look at the results for total pore volume, and we've tabulated these. For vacuum degassing at room temperature and 50 degrees, we've already seen that the longest degassing time at 50 degrees achieved the target BET surface area. With pore volume, more degassing conditions fall within specification, meaning that they exceed the minimum value of 0.53 cc's per gram, but none actually match that of the baseline sample. And that really is our target here, and that had a pore volume of 0.61. So it's safe to say that it's only really the 18-hour degassing at 50 degrees C that provides an acceptable pore volume result in comparison with that. Pore volume results for vacuum degassing at higher temperatures follow the BET surface area results very well, with acceptable volumes being obtained after 6 hours degassing at 100 degrees and 3 hours at both 150 and 200 degrees. So it's quite clear that degassing time is significantly reduced with the application of heat, and this really should be the preferred approach whenever sample integrity allows for it. Flow degassing. Although we obtained acceptable surface area results at each of these temperatures, pore volumes remain a little low compared to the vacuum method. They are above the minimum specification, but we really should also be considering our baseline sample, and they're between 5 and 8% lower than this throughout. Now, as pores become larger, the increase in surface area, that is to say the surface area of the walls of the pores, actually decreases relative to the increase in volume. It is therefore reasonable to observe some disparity in the relationship between surface area and pore volume when comparing results. And it shows the necessity of considering the effects on both pore area and pore volume of extraneous volatile substances. So ultimately, we can compare the degassing times required at different temperatures using both techniques in order to obtain reliable surface area and pore volume results. With increasing temperature, the required degassing time falls. So under vacuum, this is in excess of 18 hours at room temperature and reduced to just 3 hours at 150 degrees. We can also see that at any given temperature, 100, 150 or 200 degrees, flow degassing requires a longer period than the vacuum degassing option. As a final note, it's worth highlighting the effect of having very small pores within a material. Micropores are pores smaller than 2 nanometers, and they're very common in a wide range of materials and applications, and they require special consideration. Gas adsorption can be extended to specifically analyse the characteristics of micropores, and this usually requires prolonged degassing with the application of heat. Due to the relationship between pore area and pore volume with pore size, as pores become smaller, their respective area increases relative to their volume. and so micropore surface area will be more sensitive to the presence of contamination. Now, this silica aluminum material is not particularly microporous, but we can get an idea of micropore character through the application of T-plot analysis. We won't go into that in any detail here, we'll save that for another presentation, but we found that the micropore area of the baseline sample is 8.8 square meters per gram, and so that's our target with the degassed samples. Here, we're only showing the results for degassing at elevated temperature, and we're comparing the two methods, flow and vacuum. In fact, degassing at room temperature actually failed to provide reliable T-plots, indicating that the micropores remain contaminated even after 18 hours of degassing. We can see that vacuum degassing achieves a good match of micropore area with the baseline result at the longer degassing periods. And we've included the shorter degassing periods at 100 degrees to really show the progression of micropore area, or the increase in it. On the other hand, micropore areas via the flow degassing option remain low. Values aren't appreciably high, but again, that's because this material isn't overly microporous. But it would become a far more significant issue if we were considering a highly microporous material. So, in conclusion, sample degassing is an essential part of the gas adsorption analytical process. Complete degassing ensures that accurate and reliable surface area, pore volume and pore size distribution data are obtained. Pore size data are more significantly affected as pores become smaller or their size distribution becomes narrower. Wherever possible, we should apply heat to the degassing process. Vacuum degassing offers higher efficiency than flow degassing in terms of the degassing period required. And for the analysis of microporous materials, special consideration when selecting appropriate conditions are required, as these often demand prolonged degassing times. So, thanks for watching. We hope that this has been useful to you, and of course, thanks again to Philip and Ethan for their excellent work on all of this during their work placements.